Hi, welcome to the 12th, is this 12th Bad Math Day? The 12th Bad Math Day, hosted by Google. Let's have a hand for Google. Search through them, everybody. We're working on an endorsement deal right now. So just a little reminder that if like everybody else in the world, you have one of these things, you should now turn it down to off or silence, please. I went to a funeral a couple months ago where one of these went off. It was very unpleasant. So please turn off your cell phones. And let's see. So our first speaker is Dave. Dave, I've never learned how to pronounce your last name.
Dave. Oh, Beyer.
Beyer, okay. Dave Beyer of Barnard College, noted mathematician, and also co-inventor of Macaulay, program with which many of you are probably familiar, and of course, star of stage and screen. So you can ask him about it later. All right, so here's Dave Beyer talking about the coloring torus of a graph.
Hi. So for those of you who like to come to talks looking for mistakes, there are already several in the first slide. I got Ruchira's email on how to get here too late to change the directions here. Okay, so I'm interested, my background that pertains to this is toric algebra, toric geometry. I've written various papers with, say, Bernd Sternfels, Soren Popescu on applications of toric geometry to things that felt like, to me, to be close enough to graph colorings that I wanted to look again at graph colorings, which was a topic that always interested me, say, in high school. There's a standard way, so there are many variations on graph colorings. I'm interested in I'm trying to find a geometric explanation for the sort of most fundamental kind of graph colorings, in my opinion, is vertex colorings of graphs. So we have a graph G, and I'm going to consistently through this talk, I've never used once the fact that it is d vertices, because we're going to get away from vertices quickly, but I do use everywhere that there are n edges. And rather than using colors to color a graph, the typical thing you find in a textbook is to take a finite abelian group whose elements you consider to be the colors. And then the idea of coloring a graph is to assign a distinct value to each vertex, distinct in the sense that two neighboring vertices never have the same value. So to four-color a large planar graph, you'll only use four colors, but you'll never have the same color next to each other. So the first step in and the advantage to thinking of this as a group, it turns out the order of the group doesn't matter. It's standard that, the group itself does not matter. Any two groups of the same size, you can color with one or color with the other. But the shift we want to make is we want to think of this as a phenomena on edges rather than a phenomena on vertices. So this is, so we want to think of the difference going along an edge between the vertex and the next vertex. So we're looking for, so coloring induces a function on edges which is never zero if it's a strict coloring. And if you come around in a loop, you come back to the same color. So these assignments have to sum to zero around any cycle. So this shift is a lot like studying functions. You can study gradient vector fields, but if you're looking, a gradient vector field has a property that you integrate around in a circle, you come back to where you started, and it's the same thing as studying functions up to a choice of a constant. So here, if I have an assignment on edges which sums to zero around any cycle and is non-zero everywhere, I can always get back to an ordinary coloring by just picking an arbitrary value for one vertex and then propagating using the edge differences. So I'm never again going to think about vertices. Now one feature of this is it makes it clear that this is dual to another interesting concept, which is a flow on a graph. And a flow on a graph, instead of being a non-zero assignment on edges which sums to zero around any cycle, it's a non-zero assignment on edges which sums to zero in and out of any vertex. So let me show you an example. So on the top example here is a triangle, and I'm coloring with integers mod 3, and so the color I use is 0, 1, 2 on edges, on vertices, And that corresponds to the difference function. If I orient each edge counterclockwise, as I've shown you, it corresponds to the difference function 1 everywhere. And that's 1 sums to 3 going around the cycle, but that's 0 in our group A. The dual flow would be to draw the planar dual. I haven't drawn it quite the same because of the outside is now at the bottom over here. By just sort of turning everything quarter turn and labeling that edge with the same flow. Instead of getting a labeling of edges which sums to 0 on cycles, I get a labeling of edges which, whose flow in and out of each vertex is 0. So we have a total flow of 3 into the bottom vertex, but that's 0 mod 3. And so the second example is just a more elaborate version of the same thing. So how do people... The first way I thought about how to count these, which is, I mean, implicit in most book descriptions of, say, calculating the chromatic polynomial, is you can imagine a hyperplane arrangement, but not over the real numbers, instead in the integers mod mz. And the idea is you want the space to be the set of all possible edge labelings which sum to 0 on every cycle. And then you want to put in a hyperplane in that space for everything for every rule you're trying to obey, which is don't be 0 on this edge, don't be 0 on this edge, don't be 0 on this edge. So for this example, and then you can try to do inclusion-exclusion counting or more fancy Möbius inversion counting to try to figure out if there are any vertices left uncovered by your hyperplanes. If you can find a vertex, you can find a point in your space which is not covered by any of these vanishing hyperplanes, you found a coloring of the graph. I uniformly find it easiest, even though for counting purposes you leave it the way I just said it. I find it easiest to look at these things if you take the universal cover. So always use a cyclic group, since the exact structure of the group doesn't matter, just the size of the group. And embed that cyclic group in the unit circle, and then we can take the universal cover of the space of all group valued functions, which sum or 0 around any cycle, as a real vector space of all real valued functions which sum to 0 around any cycle. And in that space, I can draw my original edge functions. So all these little dots, the dots on lines and the dots with red circles around them, are functions from edges of the graph to z mod 3z in this case. And then saying that you can't vanish on A, you can't vanish on B, you can't vanish on C, is just saying void. You have to avoid those green lines, which are our hyperplanes in this case. And so this is the same pattern. This is a periodic pattern, so there are really only 6 distinct points in the orbit here as you orbit around, but I just prefer to think of it periodically. So the strict colorings are the ones that are shown not in any hyperplane. Okay, so how has this been generalized? There are many generalizations of vertex colorings. There's edge colorings, there's list colorings. My favorite it was first called the star chromatic number by Vince in '88, and then was later, it's been called more recently the circular chromatic number, starting with Chu in 1992. And the idea, it actually, by accident, fits well. You can think of, this actually would make sense coloring a real map. There is a color wheel, and so the actual pigments actually tend to, you can think of pigments as having the topology of a circle. Actually, it's more complicated than that, but you can imagine a circle of colors, and you want to use lots of colors, and you don't really care that over here it's a different shade of crimson than over here. What you want is the colors to be as far apart from each other as possible along common borders. So you don't really care about if ink is cheap now, because we don't mix individual pigments when we print a map, we use 4-color presses. But the 4-color presses are synthesizing lots of colors. If you want colors to be as far apart as possible in the color wheel, then this model starts to make sense, where we think of our colors as having a cyclic ordering, and instead of saying never have the adjacent vertices the same color, say I want adjacent vertices to be as distinct as possible. So it happens for a pentagon that I can optimally color a pentagon using 5 colors with a separation of 2. And 5 halves is less than 3, so that's actually better than 3 coloring it. And you can't 2-color it. So people think that this more naturally reflects the character of how you color a pentagon. So the circular chromatic number, the idea was, well, what's this with, mixing? There's also a notion called fractional colorability, which is not the same notion. So it's sort of like domain names. Somebody got the website first. I think that this should be called fractional colorability, but that's a different concept. So circular colorability, what Chu came along and said is, well, why not just use the unit circle itself and measure how good a coloring is by what the separation is along the unit circle between any two neighboring vertices. So it's a more geometric formulation, but it turns out to be exactly the same theory. So I want to go back and look at the first example. I'm using the same ambient space, which is for this triangle, I can draw it in the plane. It's a set of all maps on edges, real valued maps on edges, which are 0 around every cycle, as in 0 around one cycle here. So actually, if you think of this in R3, this is the anti-diagonal plane in R3 that we're looking at. And then if I want to simulate four coloring using the real circular colorability, then I would protect each edge not by a hyperplane, but rather by a slab of radius 1/4 each way. So that any point that's within a quarter in any coordinate of one of these hyperplanes is a bad point, and the rest are good points. Now the reason this gives the same theory as before is because the adjacency matrix of a graph, basically the bond lattice and the cycle lattice of a graph are examples of unimodular lattices, which basically means that the matrices in sight here only have unit determinants. So that if we try to calculate what the coordinates are of one of the vertices of these air pockets here, we're introducing the only denominators that get introduced in the problem. So if we started with a denominator of 1/4 because we made our slabs 1/4 each way, then those vertices of those air pockets are all going to have denominator 1/4 also. So in fact, they're effectively integral with respect to the grid we're thinking about. And so just starting with a circular definition, you get back to getting rational answers just like the first definition. Okay, so what have people done with circular colorings? Well, there's roughly 100 papers between MathSci and Archive and searching for earlier names for this. And there's a good survey that came out 5 years ago by Zhu in Discrete Math that describes a bunch of problems. And I guess my favorite theorem, I don't know if it's a representative theorem or not, is using the existing four-color theorem. The point of view of all this work tends to be that the true colorability of a graph is this rational number that we're constructing here, which is the best coloring with this flexibility of using fractional distances and so forth. And that when people discuss the integer colorability, they're wrong. I mean, they're approximating. We don't want to work with the approximation anymore. We want to work with the actual value. So I mean, if I were to paraphrase the theme that seems to run through all the work is it's reevaluating everything that's been said about colorability of graphs and going back and saying, well, if we look at the true answer, what theorems can we now prove about the colorability of graphs? And so it's interesting that every possible rational number of a planar graph between 2 and 4, 1 also occurs in a degenerate case, but every rational number between 2 and 4 occurs as the circular chromatic number of a planar graph. So they're dense everywhere, and that's kind of nice. Okay, so what am I interested in doing? The view I'm taking here is since I'm coming from toric algebra, and in a nutshell, what is a toric variety? I mean, the circle is just the simplest torus you can think of. You're modeling the real line by a lattice, a one-dimensional lattice. And in studying other tori, you're just taking higher dimensional real spaces and modeling out by other lattices and so forth. So I'm thinking that this theory of circular colorability is like one variable calculus, and I would rather be doing multivariable calculus or calculus on manifolds or whatever. So I'm looking for a way to tie in the toric geometry I'm interested in into the study of graph colorings. And circular colorability to me looks like an in. So there's a design pattern in mathematics, which is, an example of which is the Jacobian of a curve, is that you never study a problem by itself. You try to find a parameter space of possible problems of which the problem you're interested in is simply one instance. And then if you can prove any interesting theorems about the parameter space, maybe what you wanted to know about that one instance will fall out of the more general results. With that in mind, it led me to this definition so the first shift, if we review, was instead of thinking of vertex colorings as actually values on vertices, we thought of them as values on edges. And then it's equivalent as long as we make sure that we sum to zero around cycles. Well, the next shift is instead of saying we want to avoid zero, let's say we want to be as close as possible to some different target. So this is actually a very easy shift to make for the original problem, which is in a circular coloring, if I said that my target is 1/2 for every edge, and that I may rarely be able to achieve a difference of 1/2 on each edge. In fact, I'm only able to achieve a difference of 1/2 on each edge if the graph is too colorable, which is an extreme case. But more generally, I might be able to get uniformly close to 1/2 on every edge and still have all the cycles sum to zero. And that's my shift. Instead of worrying about avoiding zero, I want to get as close as possible to 1/2. And then the more general problem I want to study is instead of studying 1/2, 1/2, 1/2 as the target values on edges, I want to study arbitrary target values on edges. So that gives me the first sort of working definition, sort of more as an exercise to work out, is no detail, is I would define the coloring torus of a graph to be the space of all, R to the E, which is the space of all functions on edges, which nominally are a raw target function for a process like this. But then I want to mod out, here's my torus coming, I want to mod out by whenever two problem statements are actually equivalent. Okay, so let's see some examples to see how what that looks like. So in this example of a pentagon, I'm rephrasing the example we had a few slides back, where I showed the 5/2 colorability of the pentagon. Only instead of wording it with integers mod 5, I've now said that in blue around the upper left pentagon, I'm writing down my target values, that I would like to come up with an edge function which is as close to 1/2 as possible on every single edge. And the edge function I'm actually able to come up with, which is directly transcribed from the previous example, is to assign a value of 2/5 to every edge. And now 2/5 sums up to 2 when you go around the cycle, but we're modding out by integers, so 2 is 0. So that is a valid coloring. And the distance that I get between 2/5 and 1/2 is, is a tenth, but you have to translate that back to the other notation if you care to describe to somebody else, well, I 5/2 colored this. But my point of view now is to forget that completely. All we care about is distance between target and coloring. So if everyone remember what it means, if I was trying to four-color a graph, I would want to find coloring within a quarter in this metric of the target coloring 1/2, 1/2, 1/2, 1/2, 1/2. But I want to study more generally what is the metric properties of the coloring torus. Okay, so if you look at the middle example on the top, it's actually the same example. And the way you can see that it's the same example is if you look at what I did on the upper right, I've added 1/2 going out of the top vertex both ways, and I subtracted 1/4 going out of the bottom left vertex both ways. Those are both examples of bonds. So I'm actually acting on this by the real bond lattice, the real span of the bond lattice. And what I've done is I've moved my target value. So instead of being 1/2, 1/2, 1/2, 1/2, 1/2, it's 0, 0, 1/2, 3/4, 1/4. And simply by sliding my coloring with the same moves, you'll notice that these changes have the property that if I sum them around the cycle, the changes are just 0. So those are legal changes which don't change a coloring or a target, really. You could do it to either or both, and you're really having no effect. So the middle problem, in our coloring torus, we should really think of the middle problem and its coloring solution as being entirely equivalent to the left problem. Yeah?
So this is like homology or cohomology or?
There will be a homology in this talk at some point. What?
In general, repeat the questions for the middle.
Oh yeah, is this homology or cohomology? And yes. Yeah, I will formulate it as a cohomology group. Although I find it easier to understand, more viscerally. Whatever. We'll get to it. Okay. So the bottom is another example, which is the first triangulation of the sphere, which is the tetrahedron. I put the standard coloring problem down, which is a half on all edges. And I'm able to get, and there's an optimal coloring. It corresponds to a 4 coloring, but this is what it looks like in our language. And you'll notice that there's a tight little loop where we're off by a quarter going around an entire loop. And then there are actually 2 places, and you can find the loop quite easily because there are 2 places where we're actually using a value of a half. So we're on the nose reading our target on 2 edges. But the other 4 edges forming a cycle, we're off our target by a quarter. And if we were to try to flip to if we were to try to add 1 various places and flip to a different lattice point, we'd still be off by a quarter. This is an extremal, this graph is just 4 colorable, even in the real sense, and the fact that this is as close as we can get for that target. On the other hand, on the lower right are a different set of target values. All I've done is one change. I've moved this to a different point in the coloring torus by assigning the top vertical edge a target of 0 instead of a target of a quarter, and instead of a target of a half. And the effect that had was I can now come up with a coloring which is within a distance of 1/6 everywhere of the target, which is much closer than a quarter. So that's a better coloring. The closer you can get to the target, the better your coloring is. Okay. So we can go back and look at this in terms of ambient spaces, and I actually find this a little bit surprising, but one way to interpret this target coloring model, if you're used to the hyperplane model for the original one, is to instead of having, if you remember in our earlier pictures, the slabs all corresponded to a central arrangement. I mean, all the slabs pass through the origin, and then you have the periodic translates of them, but they all pass through all the translates of the origin. Whereas when you start moving around the targets so that they're not neatly lined up on a half, what it corresponds to is letting the slabs sort of float freely in space to different positions. And for a different arrangement of the slabs, are there still air pockets? Now, I mean, at the end, I'm going to show you some evidence. I find this surprising because I would think that to try to cover space with a given, so what are you, if you view this as a game, we're trying to cover space. And we're given a slab thickness, and we're given the underlying hyperplanes of our slabs. All we're allowed to do is translate them. You'd think that it would be having one hand tied behind your back to have have the arrangement be central. You think that by having all the slabs overlap at the origin, they'd be leaving gaping holes elsewhere, and you could cover those holes quite easily by having the slabs float away from each other to more uniform. I mean, am I making sense? That's my intuition. Wouldn't that be your intuition? Well, it turns out, at least in planar graphs, that it doesn't seem to be the case. I'll make that statement more precise later, that somehow, even when one affords this greater level of flexibility, it proves to be just as hard to cover space, or conversely, you leave gaps just as often and therefore can color just as often in this more general model. So that's starting to suggest the conjectures I'm heading towards. Okay, so this particular example, even though I chose the point 1/2, 1/2, 0, that's equivalent, again by a bond move, to 0, 0, 0. So in fact, metrically, the target is itself a coloring, so we can get distance 0 from it. And in fact, the center vertex of each of these hexagons is a coloring which is distance 0 from the target, which corresponds in our original language to a 2 coloring. So this just sort of shows the flavor of how you might think of this geometrically. Okay, so how do I construct the coloring torus? How do I sort of make more precise the implication that there is an equivalence relation among edge functions that I want to be using? Well, this is the same lattice that anyone who studies this using toric algebra would use. There's a bond lattice in z to the n. Bonds are also thought of as cuts. I mean, think of minimal ways that you can take scissors and cut a graph along edges into two pieces. If you put functions on those edges, all pointing from a given side to the other side, that's an example of a bond. The simplest example of a bond is a vertex bond, which is you charge a toll leaving a vertex in all possible ways. Or what New York City does is charge a toll entering the city in all possible ways. But those are examples of bonds. So for example, for G equals K3, I show the 3 vertex bonds. They actually are dependent. You only need any 2 of them. But that defines the bond lattice for that graph. So the full equivalence is we saw an example of moving by a real multiple of a bond in the previous example of an equivalence. And built into this whole picture, because we're coloring with R mod z, is anywhere there's an integer, you can move it to another integer. So if you add those 2 statements together, you actually get the full equivalence group for this setting, which is RL plus z to the n acts on R to the E, R to the Rn, and 2 coloring problems are equivalent if they differ by an element of that group. So a coloring is simply, coloring happens to actually be an element of that group. And then we're basically comparing that subgroup to various cosets of that subgroup. So the problem we're interested in is we want to be able to calculate in the L infinity norm, which means take the max of all separations. What is the distance from a problem alpha to a coloring beta, where the L infinity norm is induced from Rn. We take all possible differences in any coordinate in Rn and take the max. But we want to build into this somehow the equivalence that's determined by RL plus z to the n. Okay, so let me go back and say, what is the, how do I translate this back to ordinary colorability? This is just a bit of algebra that we could say that a target problem alpha is 2 over 1 minus 2r colorable if you can get within distance r uniformly across all coordinates for some beta which is a valid coloring. Okay, so I guess what I want to formalize this by just defining the subgroup H to be that group, and then I can restate everything in terms of that subgroup. That basically, what does it mean to be an H? First of all, it's closely related to what the bond lattice is in the first place. An element of H is a function on edges, and it's a function on edges that sums not to 0 but to an integer around any cycle. And in some sense, it's easiest to think of this in terms of the universal cover of everything we've been doing when we fold it. And so we're saying that an element of the space Rn is 2 over 1 minus 2r colorable if the distance to the nearest point of H, think of H as this periodic set of subspaces, the L infinity distance to the nearest point of H is less than or equal to r. And you could rephrase that as the distance between the coset H alpha and H itself is less than or equal to r. And I want to define the coloring torus of T sub G to be Rn mod H using this induced metric. Okay, so now let me answer your question. Okay, there is a homological interpretation of this. I remember learning deformation theory. All the cool things they did were H1 of something or H2 of something. So one tends to look for this. But I think this would be most useful for generalizing this to other settings. But I don't know why one would do that. I've tried that. Basically, I want to view a graph as just being a one-dimensional simplicial complex. And the fact that I've chosen an arbitrary edge orientation. There's nothing special about the directions I've chosen for my edges. I just need to make some choices everywhere in order to do calculations. And we'll discuss that later. But that corresponds to orienting the one simplices in the simplicial complex. And then the bond lattice that we were studying before, we can recognize as being the image of the co-boundary map. So if we want to calculate cohomology instead of homology, then we want a way of lifting functions on vertices to functions on edges. And the way we do that is delta of f is defined on each edge as being the difference of the values of f between the two edges, between the two vertices it came from. So that's used to define the ordinary simplicial cohomology of the simplicial complex. So the familiar cycles come out of that. But what we can do is you can use any group you want to construct cohomology. And the natural group to consider here is to plug in our color values. Our color values are the circle S1, but thought of as a group, it's R mod Z. So we can write down the chain complex R mod Z to the V is mapped by the co-boundary map to R mod Z to the E. And R mod Z to the E is really just Rn mod Zn, right? Because n is the number of vertices we have. And we're modding that out by the image of the real image of the bond lattice. So it's really our first definition from before that the coloring torus is simply simply H1, the first cohomology group of the graph with coefficients in the color group. So, and then of course, the way in which we talked about inducing the metric is you minimize the distance between two cosets, taking the L infinity norm, and there is a distance measure which you can apply directly to H1. That all works here. So in terms of original language, the distance between alpha to 0 determines the colorability of alpha. And the first problem we started with, which is what is the ordinary colorability of a graph, is the distance from the vector 1/2 to the vector 0 in this space. So now you could apply this to other coloring groups. It might be interesting to go back to discrete coloring groups and try this definition. I'm reminded that Rhoda tried hard to prove the four-color theorem not by using, by using pairs of binary colorings. I don't know if anyone remembers reading that stuff. And I never really quite understood what he was trying to do. But it suggests that possibly it could be of interest to study different structures besides a purely cyclical structure. In any case, if one plugs in a torus, and instead of coloring on, you could iterate this. You could actually plug in the coloring torus itself here, and everything works formally. And you could, I'm not sure whether there's any theorems that would come out of that, but this coloring torus is a general construction which we're using in this one special case for circular colorings. Okay, so let's do some examples. So the simplest example is where there's one cycle. So again, I'm going to take a pentagon. And I want to, just for the sake of definiteness, orient everything clockwise and label the edge values x1 through x5. And what is our bond lattice? Well, we have two equivalent formulations of the bond lattice. We could think of the bond lattice as generated by the vertex bonds, or we could just take the condition that the bond lattice is the set of integral points in functions that sum to 0 around any cycle. Well, there is only one cycle. So functions that sum to 0 around this cycle is just functions that, some of the coordinates are 0. This is, in other words, L is the anti-diagonal hyperplane. It's easier to picture it for the triangle. It's just the anti-diagonal hyperplane we were looking at before for the triangle. So the coloring torus is we take Rn, in this case it's 5 space, mod all integer translates of that anti-diagonal hyperplane. So what you get is you get closely spaced together translates of the anti-diagonal hyperplane. And when you mod Rn out by that subgroup, you get as a quotient group a circle which is covered by just a single segment going from one hyperplane to the next copy. So in fact, in the middle of this slide here, I'm drawing you what the actual circle looks like. Now I'm insisting that n be odd just to show you that in the odd case that the ordinary coloring problem 1/2 is as far as possible around the circle from 0 as possible. So I give examples of, what are various representatives for 0. Basically any integer point in Rn mods out to 0 in this quotient. And the point of all 1/2 mods out to the same point as 1/2 and all zeros. Because it's, like an even number of halves adds up to 1. I can slide around using bond moves. And I can smooth this out completely using bond moves and just spread out that single value of 1/2 across all entries and make it 1/2n, 1/2n over 1/2n. So in fact, we know the distance in this, it doesn't feel yet like a L infinity norm because we're only in one dimension. All norms pretty much look the same in one dimension, at least this kind of norm. And so we're only taking one difference. It looks like a circle where it's 1/n to go all the way around and 1/2n to go halfway around. So in fact, for this kind of graph, the ordinary coloring problem is the hardest coloring problem there is. And the answer in terms of circular colorability is that an odd graph is 2n over n minus 1 colorable. Notice the limit as n goes to infinity, that value approaches 2. So since these are odd, you can only 3-color an odd graph using the ordinary definition. But if you try to 2-color a graph, you almost get away with it. Imagine a million vertex graph, a million gone. You go, okay, red, right, red, white, red, white. You get almost all the way around before you get in trouble. And the discrete definition says you're screwed. I mean, you were just, what you do is wrong. Whereas the continuous definition says, no, just take that little gap and smooth it out. And if you smooth it out over all n vertices, then what you end up with is what this is saying, which is that that it's actually very close to 2-colorable in the real sense. Now, there's another phenomena here, which comes up again in the next slide, which is a well-known property of bond lattices and cycle lattices, which is the cycle, which would be the value 1, 1, 1, 1, 1 on these edges, is actually not the next hyperplane. It's actually 5 hyperplanes out. Okay? So in other words, a way of saying this, I think if anyone could tell me a reference for this, I've read this various places and I can't find it anywhere. But I mean, it's a well-known fact among people who study lattices on graphs, is basically if you take the bond lattice on a graph and add to it the cycle lattice on a graph, you get a full dimensional lattice, but one that is finite index in the full lattice. And that index is well known to be the number of spanning trees of the graph. So here we can get a spanning tree by deleting any one of the 5 edges. There are 5 spanning trees, and sure enough, the cycles give us index 5 in our family of hyperplanes. Okay, so the next example is not an example we would study for ordinary coloring so much, but becomes interesting in this case. I mean, notice you generally leave out self loops and multiple edges when you're doing coloring problems in the ordinary case. But this definition, it makes perfect sense to at least ask, well, what's going on if we allow multiple edges? So this is dual to a triangle. You could also say we're studying flows on the triangle. So that's where these intuitions would come in helpful. So dual to the triangle, we have 3 parallel edges from the bottom vertex to the top vertex. And now the bond lattice, now it's easier to think in terms of vertex bonds. All but one generates, so there's 2, so all but one is just one of them. So we take one vertex bond, which is let's have the value be 1 on each edge going up from the bottom. That generates the bond lattice. So the bond lattice is 1, 1, 1. So my picture is I have R3 with this diagonal line in it, but then I have all integer translates of that diagonal line. And if I squash all integer translates of that diagonal line, mod out by this, I basically collapse R3 to R2, and I get this triangular pattern, or hexagonal pattern, however you want to think of it. It looks like a sphere packing of each of those lines quotients to a point. And again, I've drawn in blue the lines that correspond to cycles. And I've drawn in red the rest of the lines. And you'll notice that the cycles are index 3 in all the lines. It's another example of that same phenomena. There are now 3 spanning trees to this graph. Knock out any one of the 3 edges. But from our point of view, it's not simply the cycles that matter. It's Zn, modulo this, RL. So what I'm looking at, since it's harder to describe, I can't simply draw you a circle again. But the easiest way to picture the 2-dimensional coloring torus is via its universal cover. So this is, what I've drawn here is, in the lower left is a big portion of the universal cover of the coloring torus. And on the right, a blow up of a couple of vertices of the coloring torus. So each dot is the same origin. I mean, we're basically taking, we constructed the torus by modding out by a mixed group. It had a continuous component, a vector space component, and a discrete component. I prefer to think about all tori as being some vector space modulo a purely discrete group. So that's the picture we have here when you take the universal cover, is that we take that planar R2 modulo that discrete group, which is the dots, and that is the coloring torus. So what happens, how can we think of this metric? This is a polyhedral metric. Upstairs, we have little cubes around things, and the unit ball is replaced by a unit cube. But now that unit cube is being quotiented by this diagonal line. And so what happens when you take a cube and you squash it with antipodal points getting brought to the same point? A unit cube squashes to a hexagon. So in fact, what you see in gray here are hexagons which are expanding unit balls around each of these origins. And what we end up with is a Voronoi diagram. So the hexagons going the other way, which are in green, are the region boundaries where there's a hexagon of points which are closest to a given origin in the universal cover. And so this midpoint here is the closest point between these 2 vertices, but it's still much closer to either of these vertices than going on. So what we end up with is an interesting idea, which is the antipode, which is you can look in a coloring torus, and instead of asking for a particular known problem you want to solve, ask what are the worst problems for this graph? There may not be a unique worst problem. In general, this polyhedral metric is going to be very convoluted and complicated, and there'll be many, many pockets which are further, like there's a place between the Earth, Sun, and Moon where gravity stops and dust actually collects there. There'll be many, many pockets in these universal covers where you're equidistant from a bunch of points. And those are going to be the hardest coloring problems. So in this particular case, I've drawn an example where you take the line from here to here, you can see that a third of the way up is this pocket. And what that translates to is a target value of 0, a third, and 2/3. And there's just no way to make that target particularly happy, right? I mean, because any coloring of this graph has to sum to 0 around every cycle, which is basically the same thing as saying it has to be some multiple of the generator of L, which means we're going to give the same value on all 3 edges. So it's basically the coloring problem simplifies to pick a number and get as close as possible to 0, a third, and 2/3. So okay. So as I said, I prefer not to think in the total space where I'm modding out by both a vector space and a discrete group. I would much rather understand more generally what this collapsed cube looks like in each of these, in my coloring torus universal cover. So it turns out that the answer is closely related to Minty's theorem, which keeps coming up, partly because what Minty's theorem really is, if you're a fan of oriented matroid duality, I mean, it's really it's a simple application of matroid duality is why it seems to come up in lots of cases. But Minty was interested specifically in ordinary M colorings of vertices of graphs. And he proved in '62 that one criterion for a graph being M colorable is that there be a way of assigning edge orientations so that as you went around every cycle and looked, how many edges are going the wrong way, how many edges are going the right way, that the ratio is fairly balanced. by which he means, say you're trying to four-color a graph, and you went around a cycle with 8 edges, then at least 2 have to point forwards and at least 2 have to point backwards. Or in other words, at least a quarter of all edges have to point forwards, at least a quarter of all edges have to point backwards. And you need such an edge orientation for all cycles in your graph, and that's equivalent to there being a four-coloring, an M-coloring of the graph. So for people who studied hyperplane arrangements, this is a familiar pattern, or generalizes a familiar pattern. I want to go back to my very first slide where I showed ordinary colorings of K3. And now I want to pick an origin and just look around, look at the chamber structure around that origin. The plane in which these triangulation appears is the plane of functions that sum to 0. They're edge functions. They sum to 0 around cycles, but they're edge functions. So that each chamber near the origin is, since it's a chamber, is assigning a sign to each edge, whether that function is positive or negative on that edge. And we can compare that sign to the reference orientation we needed a reference orientation to make calculations. And what we effectively can do is we can look at each corner near the origin and from that just write down an orientation of the graph, which is like the street address in matroid theory sense of that corner of that chamber. And you'll notice that if you do this for this example, that you only get 6 edge orientations. You don't get all 8. The 2 that are missing are the 2 cyclic orientations. Okay? So, the well-known phenomena for hyperplane arrangements of this sort is that your non-empty chambers, if you make a central arrangement instead of a periodic arrangement, are precisely the acyclic orientations in your graph. And so what is an acyclic orientation? Well, basically, in Minty's language, it's simply a way of assigning directions to every edge so that around any cycle, there's at least some edge going the wrong way and the right way. You can't have all the edges going the same way. So Minty's theorem is like a quantification of making that more precise. Instead of saying there's got to be at least one edge each way, you say there's got to be at least 1 over m edges each way. So generalizing the idea that the non-empty chambers in this arrangement are acyclic orientations, the fat chambers that actually contain lots of colorings are the well-balanced orientations. Okay, so again, I'm temporarily flicking a switch and turning off the plus z to the n. If you remember, my definition of the coloring torus was to mod out by RL plus z to the n. I'm flicking that off as if I'm working in the, just to get the metric. What I want to do is understand this one effect, which is what does the metric look like when I mod out by RL? So upstairs, before I mod out by RL, if I have a point alpha and I want to know how close is it to the line RL, well, I can probe that question by making a box of radius r, so it goes from alpha minus r to alpha plus r in each coordinate. And then I want to ask, does that box intersect the subspace RL or not? Okay, so this is going to turn out to get Minty's theorem, among other things. So basically, a knee-jerk reaction for anyone trained in polyhedral combinatorics would be Farkas' lemma here, which is that either the box intersects RL or we can separate the box from RL using a hyperplane. Okay, so to formalize that slightly better, we might as well choose a linear functional that vanishes on RL. And then the way of restating that is either the box intersects RL or I can find a linear functional vanishing on RL that is strictly positive on the box. That's really saying the same thing. Then just take the linear functional equals epsilon and there's your original hyperplane. Okay, well it happens that we know what these linear functionals are in this case because RL is defined by the vanishing of the cycle sums. So any linear functional vanishing on RL, the coordinates we want to be using here are just going to be sums of cycles. It's a linear combination of cycle sums. Now, the cycle sums have an important property, they're actually the circuits of a matrix. I mean, in other words, you can picture them as being all minimal intersections with the coordinate planes of some subspace. Or more familiar language for toric people, I mean, since the matrix in question is unimodular, this is actually the Graver basis of a matrix. But in particular, what's the take-home message? What you really need to know about it is not only can you express any of the linear functionals we care about as a combination of cycle sums, we can actually do so conformally. In other words, first take your linear functional and jiggle it so that it's non-zero on every edge. Then you can break it down into a sum of cycles with that sign pattern for every single cycle. Okay. Now, moreover, since it's a cube lined up with the coordinates, once we have a sign pattern in mind, for our original linear functional, we can canonically decide for any functional with that sign pattern, what is the lowest vertex? Just, edge by, side, coordinate by coordinate, just look at the sign and say, okay, let's go low, not high. That picks out a corner of the cube. So basically, for any linear functional in that space, in that orthant, it's going to have a minimum value on that corner of that, on the given chosen corner of the cube, which we decided is the smallest, the minimum corner of the cube. So now, if you have a conformal sum of things like this, and the sum is positive, at least one of the pieces of the sum has to be positive. So what have you just found? You found a cycle that is positive on that vertex, but it has the same sign pattern we started with, so it's even bigger on all the other vertices. So we have a cycle which separates the cube from RL. So we end up with a very clean description of how to tell whether a cube meets RL or not. Either the R ball around alpha meets RL, or some cycle is strictly positive on the R ball. Okay. So if you were zoning, this is a place you could just start from scratch. I love this problem just as its own problem. I mean, if you like little linear programming type problems, here is a puzzle. You have a graph. You have intervals of valid values you're allowed to assign to each edge. Can you come up with a choice of values from each of these intervals with a property that it sums to 0 around every cycle? Now, in terms of our previous language, you could imagine making a rectangular box by taking the product of these intervals, and then I'm asking, does that rectangular box intersect RL? That's really saying the same thing. So what we found from before is that exists a solution to any such restricted linear program like this, if and only if the Minkowski sum around each cycle contains the origin. In other words, yeah. So that's the form in which we want to be able to use this. And here we take the Minkowski sum around the outer cycle, and we get 3, 7, which doesn't contain the origin. The outer cycle. Another way of saying that in terms of the previous proof is that the outer cycle separates the cube from RL. So actually, to go back to Minty's theorem, how does this relate to Minty's theorem? Well, I've been saying the coloring corresponds to the distance to 1/2, 1/2, 1/2, 1/2, 1/2. And you can apply this criterion to find the distance of 1/2, 1/2, 1/2, 1/2. But 1/2 is an arbitrary vector because it depends on our arbitrary choice of orientation on the graph. So we go back and do what Minty wanted us to do and try all possible orientations on the edges of the graph, and then go back and again measure distance using this rule, and you'll get an M coloring if this rule ever gets us close enough by this definition. So let's apply this to our problem. We want to find out, we want to know when alpha is within R of RL. So I make a radius R ball around alpha by taking intervals alpha minus R, alpha plus R on each edge. And the box intersects RL if the Minkowski sum contains 0 around each cycle. But I can do the Minkowski sum out, and I get this expression here. And when I clean up that expression, I basically get scaled cycle sums. So that the polyhedral metric that we saw in examples before always has its facets given by cycles of the graph. And the scaling is you have to scale by the length of each cycle and then just take the sum of the values in those edges. That scaling means we leave unimodularity, which makes the problem much harder. This is a complete description of the metric. I view this as a complete self-contained description of the metric on the coloring torus, where we can work directly on the torus or its universal cover and forget the scaffolding where we're working in functions on Rn. Okay. So the special case I'm interested in is planar graphs. There's been some developments recently. I mean, the first computer proof drew suspicion in many ways, but just because it was so complicated, people didn't know whether to wonder about the code or wonder about everything else. But people believe it now. And they believe it now in part because it was redone in '96 by Robertson, Sanders, Seymour, and Thomas, and they came up with far fewer cases to consider, still something like on the order of 800 cases. Not something one could really do by hand, even on an hour commute somewhere on the subway, every day for years. It's just, and if one did, you would have checked 800 cases. You wouldn't really feel that you understood the problem. What's interesting is that these cases, the approach in both of these is similar and related to an idea that's close to 100 years old. There's a new work, I'm not sure if everyone's even heard of it, by Gonthier and Werner in 2004. There's a theorem prover, a proof assistant called Coq, developed at INRIA, Sophia Antipoli, I think. They do a lot of great stuff, like the programming language of Camel. And the idea is that a totally new proof, they walked through a mechanical, this is like the formalization of mathematics, except it needs a lot of help from us. They actually were to walk through from first axioms a proof that the computer could check. It's way too long for a human being to read and check, but a human being basically programmed this proof, which the computer checked. And there was an interactive process where they tried things, and it's just like analogous to writing more efficient code. One writes more efficient, axiom bases, and then it goes further. And the reason that people find this more satisfactory, or at least those who do, is because this same system has been used to check many things. It's not like you have to believe in code that was written once to prove one theorem didn't have a bug in it. You can believe that if there was a bug in this code, it might not have come up in this application, but maybe somebody would have found it in a different application. Okay, well, I mean, I would like a human understandable proof, or actually, let me be more concrete. I would like a proof I can understand. I mean, this distinction came up, proof of the geometrization conjecture. There are combinatorial topologists who don't really understand that proof, for example, right? Any case, looking at the coloring torus, the first conjecture I would like to make, and I find this a surprising one, is the point half, half, half in the coloring torus is just one of many points with the denominator a quarter. And I believe that every point with the denominator a quarter is four-colorable by the definition I've made. In fact, that relates to a stronger observed empirical pattern. Let me be very precise what I believe is true. I believe that it's certainly established that the radius of the coloring torus can be greater than a quarter. I mean, it'd be nice to have a little pigeonhole principle where the reason the four-color theorem is true is there wasn't enough room. But that fails badly. I mean, the coloring torus for planar graphs can be nearly a third. What I believe is the case is only the third in the limit. I mean, you can have an infinite graph, if you could define it right, it would be a third. And for any finite graph, you can have points which are nearly a third away from the origin. But there's a bizarre numerology to the denominators of the points that get closer to a third. This is like astronomers' data. I mean, the astronomers will look at some output from some computer analysis of some radio waves and then say, the universe does this. And I wish I had an astronomer to tell me what this means. Because it doesn't work for 2 and 3. But starting with 4, it kicks in. And the pattern is you can predict exactly the furthest you can get away by back solving this 5/6 times 1/3 gives us 5/18 the distance that 6 torsion points are away. I mean, one could imagine attempting a proof along the lines of you know, every antipode has the following structure, and you know, a trip through a 4 torsion point to the antipode, when you multiply it by 4, it just looks like the original trip. You know, that almost explains these numbers, but it's not quite that simple. I mean, for example, so I have ideas why this might be true, but I wanted to present the basic picture, and I don't know why it's true, but I believe it is true. So thank you.
So, any questions? All right. There we go.
Can you comment a bit on what the situation is for infinite graphs and PQ colorability?
No. Could you repeat the question?
No, you have to repeat it.
It would help if I knew it first.
I guess earlier in your talk, I guess you had this characterization result that said that all the rationals can be achieved between 2 and 4?
Yes. Oh, I see. Okay, so you want to know, the question is whether there is work on infinite graphs and circular colorability. You called PQ colorability.
Oh, yeah, sorry.
Right. I heard that, I thought, whoa.
The reason I'm wondering is in the case of infinite graphs, you have a limiting situation where you have, well, I don't know. I mean, are there situations where it makes sense to think about irrational colorability? I don't know, as limiting cases in infinite graphs.
Okay, so the question has to do with whether one could construct an infinite graph whose circular colorability might be irrational.
To be connected, then trivially the answer is yes.
Yes, right. And in fact, for strongly connected graphs, I mean, what makes it so hard to prove coloring theorems is that it's not a particularly local phenomena. But at least you can chunk it up like that. He's giving a good example. If you have disconnected graphs, just take a family approaching some point. But for say a 3-connected planar graph, which I think would be a reasonable place to ask, for an infinite version of a 3-connected planar graph, you know, could one isolate the obstructions and sew them together? I would think that you would be able to fix that. I mean, I would think that you would just be able to take. My guess would be yes.
All right. Any other questions? All right. If not, let's thank our speaker again.